To check the build of a psychrometric chart, as I mentioned before, first notice this shape. It looks like a shoe or a boot. And also notice how the x-axis here, the horizontal axis, is the dry bulb temperature in degrees Fahrenheit. Obviously, you can have a chart, psychrometric chart, that is drawn in metric system, but this is drawn in imperial system. And as you can see, this is going from 20 degrees Fahrenheit to 120 degrees Fahrenheit. If you are at this point, for example, you are measuring a dry bulb temperature or your regular temperature, room temperature of 75 because of this line coming down to 75 here. And any point on this line is 75 degrees Fahrenheit, and any point on this line, on the second line, is simply 80 degrees Fahrenheit. So if you have a point, say here, 85, and you increase the temperature, the dry bulb temperature of this point, the point travels from here to, for example, here, depending on the other changes that you have created on it as well. Another measurement that is on the chart itself is the y-axis, which is the grains of water in the air. And as you can see, it goes from 0 grains here, 10, 20, 30, all the way to 210 in this particular chart. It is important for you to remember that 7,000 grains of water equal to 1 pound of water. In the same way, 1 pound of water is equal to 16 ounces. It's just a different measurement, and it is, as you can see, a very fine increment of 1 grain being 1/7,000 of a pound. In other words, if you have a point right here, going to the right or going to the left is not going to change the content of water in that air. However, going up will increase the amount of water. We can call it humidification. And going down will simply do the opposite. It will dehumidify. It will remove water from that 1 pound of air. Now let's have another look at the diagram where we have the x-axis. We also have the y-axis. The x-axis is the dry bulb temperature in Fahrenheit. The y-axis is the amount or content of air measured in grains of water, where 7,000 grains is equal to 1 pound. You can see there are diagonal lines right here, and there are measurements on the diagonal lines where there is 20, 25, 30, 35, 40, and so forth. This is called the wet bulb temperature in degrees Fahrenheit, and what it means is if you have a wet bulb temperature of 65, your point is going to be somewhere on this line. So your point is going to be somewhere on this line. We don't know where because we have only one measurement, which is 65 degrees Fahrenheit for wet bulb. So if you tell me that air has 75 degrees dry bulb temperature, I can deduct that the point we are trying to get is here. This would be the point where the air has 65 degrees Fahrenheit wet bulb temperature and 75 degrees dry bulb temperature. Now, if we are going to increase the humidity, if you see, I can use this ruler and see what is the content of water in this air. I can simply put the ruler here, draw a line like so, remove the ruler, go here and see that it is roughly it is between 70 and 80 grains of water in that point, but it is closer to 80. I can maybe call it 77 grains of water in this case. And if I increase the humidity, I can simply increase the humidity without changing the dry bulb temperature. And I can go further, which is here, all right? And that means I have increased, the grains of water. I have increased the grains of water from 77, which is here, to let's say 103, which is here, and that is an addition of 26 grains of water. What did that do? It, as you can see, we were at 65-degree wet bulb temperature point. We went to a 70-degree wet bulb temperature point. We simply increased the wet bulb temperature, and that makes absolute sense because increasing the water content will increase the wet bulb temperature, and it also going to increase the enthalpy or the total BTUs in that air, as we are going to see shortly. One of the most important applications of a psychrometric chart is to measure the dew point of air. And dew point of air is a measurement that is also in parallel to the content of water here. It is a y-axis type of measurement, and dew point means the temperature at which that 1 pound of air is saturated with water. There is no possible way to add any more water into that air as vapor. If you try to add water to that 1 pound of air beyond its dew point, every grain you add will turn into condensation, into a liquid. So, for example, if we have a 75 degrees dry bulb, right, and 60 grains of water, so that's if we consider this to be our state point, okay, if this is our state point, one might think that what is the dew point of this state point? You can measure the dew point in a couple of ways. One of the ways is to simply draw a line to the right and go and see what is the dew point there. It's pretty much 50, 51, 52, 53 degrees. So your dew point is 53 degrees Fahrenheit, meaning beyond that temperature, you cannot add any more water. If you are at 53, you will not be able to add any more water to the air. If you try, the water will simply condensate. One more very important and applicable measurement that goes into the psychrometric chart is the relative humidity of the air that we're talking about. Let's take our previous example, which was 75 degrees Fahrenheit of dry bulb and 60 grains of water. So if we take that as our point, as our state point, what we immediately notice here is that this is between the two lines of 50, sorry, that was a bad drawing, 50 and 40%. It is though closer to 50, so I would say maybe it is 46 or 47% relative humidity. So relative humidity is 46 or 47 percent in this case. What happens if we increase relative humidity, meaning if we move this point a little bit upwards, closer to 50? Let's say we increase the relative humidity to 60%, which is here. So the point goes from there to here, and that is adding water to it. Look what happens to the grains of water. In here, we started with 60 grains of water, and here we ended up with roughly 78 or 79 grains of water. Meaning, if you want to increase the relative humidity of the air when it is 75 degrees and has 46% relative humidity, if you want to increase it to 60% relative humidity, you need to add that many grains of water to that 1 pound of air. Another thing is that relative humidity measure is also helpful in terms of calculations. So calculating relative humidity in mathematically requires paying attention to this curve here. This curve is what we call the saturation line. Saturation line is the line beyond which a state point cannot exist. So your state points can exist inside this shape that delineates that 1 pound of air, and the state point cannot be outside of that. If we, for example, go back to our point from before with 75 degrees Fahrenheit of dry bulb and 60 grains of water, this point right here, we can use this saturation line in a couple of ways. We can either push this point all the way up to meet its 75 degrees wet bulb, beyond which you cannot add any more water, because if you add water, you'll need to simply go up again, and you will need to pass that saturation line, and you're not allowed to do that. Physically, it's impossible. Or you can go to the left here and hit the saturation line, and interestingly, when you do that, you are plotting the point that we previously called a dew point. So let me explain that here. If I simply go to the left from here, in the same way I would go to the right, look how this point here, roughly 53, is the same as this point here, which is 53, and we have previously identified as dew point. So this line, this saturation line, can be used in a couple of ways. You can take your point to the left and find your dew point, or you can do that. I prefer using this horizontal vertical scale because it's simpler to see what is the temperature here. Or you can take your ruler and simply increase the temperature, increase the amount of water that you have in that air. So you can go from here to here, like so. I just increase the amount of water going there, but I cannot, this is not something I can do. I cannot go beyond that saturation line. I have to stay there. And if I do go to the saturation line, you see that I have hit the wet bulb temperature of 75, meaning this is a conclusion that if you have the wet bulb temperature and dry bulb temperature the same, you are at saturation. Another example is here, 65 wet bulb And look here, 65 dry bulb. That's saturation. That's why that point is on the saturation line. Now let's go back and have a look at how we calculate the relative humidity in this case. I am again going to start with the original point, which is 60 grains of water and 75 degrees. This is what we have, and we are roughly at 45%. It's between 40 and 50% relative humidity. Let's call it 45% relative humidity. So why does this matter? It matters because it helps you with the identification of the relative humidity concept versus the specific humidity concept. Relative humidity means how much water is there in this air compared to how much water it can have. All right, so how much water is there? Well, first of all, we just do a line, and we said that it is given that there is 60 grains of water. So we said that's what we have, 60 grains of water. But how much water can this air take? How do we find out? Well, remember there was something called a saturation line, and that for any point it is possible to go from that point to the saturation line and see how much water we can add. I'm just adding water, adding water. This is adding water all the way to here. All right, and at the saturation line I have to stop. I can see that I can add that much water. That's it. I can't add any more water to the air. It won't hold it in the air. It will simply condense. But how many grains of water did I add there? Well, if I go and make another line, because this is how we find out how many grains of water is in the air, remove the ruler, go in there, it's roughly 132. So math is telling me that I can have 132 grains of water. However, I have 60 grains of water. So if you divide what you have by what you can have as a max, that is going to give you the relative humidity in percentage, and that's going to say 45%. And I just calculated the relative humidity of that point by plotting a couple of points, starting point to the saturation point.